Yeah. So I'll talk process, and here I mainly focus on these astrophysical applications, and then I'll mainly discuss about how different model can be applied for this type of calculation and what is our model. Discuss about the results and events. Okay, so we know that one of the big question of this century is that where how these elements from iron to uranium are made, and it is now well believed that these are made through the R process nucleosynthesis, and this type of process can happen in neutron star mergers or similar environment where we have uh, high neutron rich environment. And in this process, actually, one seed nucleus keep absorbing neutrons, and then it may decay to beta decay. And in this way, very heavy system is formed. And this system then undergoes fission, and it decides the final yield of the nucleosynthesis process. And actually, fission and fragments will shape the final awareness between the mass 110 and 100. So this is some calculations of these R process abundances. Majority of the calculations are done using liquid drop models where we use liquid drop masses, and then also the Thomas-Fermi phenomenological fission barrier is to calculate the lifetimes cross sections. And here I have shown one recent such calculations. So these are basically a calculation of the fission barrier. This top row is again this final liquid drop model calculation, and then these lower two rows are HAB calculations, and this first column is calculation of the fission barrier, which decides the spontaneous fission process or the spontaneous fission half-life. Then this second column is fission barrier minus the Q-value of the beta decay. So it decides the beta delayed fission. And then we can also have like neutron-induced fission in neutron-rich environment. So this actually is the fission barrier minus the neutron separation energy. This decides the possibility of neutron-induced fission. Now we can see that these red dots are basically the final awareness at the freeze out, and we can see that there is differences between models. So different models, and also the calculated barrier. There is dissimilarity among these different models, the calculated barriers. And when these barriers are used in a network or process network, we can finally the abundance, mass abundances. These are the calculated mass abundances under different ejecta conditions. One is hot ejector or cold ejector or accretion disk. So we can see more or less the gross picture is same. And here, this peak near the mass 140 we get due to the fission fragments. But if we look into more finer details, we can see there is difference like, and this is in log scale, so there is large differences between the liquid drop calculation, so these DFT calculations. And in the DFT calculations, basically we don't get the yields directly here, so we supply this barrier to the network calculation that decides the probabilities, and from those probabilities, statistical model calculation is required to get this final yield. So there are still uncertainties, and related to these DFT calculations, what we have two limitations. One is the limitation due to the dimensionality of the calculation, like these are calculated using one-dimensional for a one-dimensional calculation, like with only one coordinate. I'll come to that. And also, we cannot have the yields directly from DFT. So these are the two limitations currently we have. And now I'm going to discuss what are the possibilities and how we can overcome all these limitations. So what we need is basically these two quantities. One is yield distributions and also the half-life. These two are the main observable we require for this R process calculations. And these are the different theories that we can apply, and I will say what theory we can apply and what we cannot for our interest. So most important, this interesting theory or most important theory for the fission study, which actually includes all kind of different correlations, is time-dependent DFT calculations, where one solves this time-dependent Kharikov-Gogolev equation, where this R is this one body generalized one body, and this H is the generalized one body Hamiltonian, one single particle Hamiltonian. So these two we obtain from the total energy density functional, and then one solve this equation. But the limitation of this kind of theory is that semi-classical theory cannot have tunneling using this theory. It actually conserves the total. And not only that, this is kind of deterministic theory, so we cannot get the distribution from this type of theory. We can have only one fragmentation if we follow a single path. Then we then left with adiabatic approaches, and then this adiabatic approach means basically this collective time scale is quite large than the intrinsic motion of the nucleons, and using that assumption we can separate the whole Hamiltonian like this. We can have separate Hamiltonian for collective motion, then intrinsic motion, and also the interaction between this intrinsic and collective Hamiltonian. Now this intrinsic part we can solve using either DFT, or we can solve using McNeek method, macroscopic method. And these actually give us the potential energy surface like this, and also the collective inertia and related quantity. And then this interaction is basically provides the fluctuation and dissipation to this collective dynamics. Now the whole question comes how to solve this collective dynamics. So there is one method, quantum mechanical method. The way we can solve is this time-dependent generator coordinate method. In this method, these collective coordinates are represented with a wave function, complex wave function, and a Schrodinger equation. A Schrodinger-like equation is solved to get the final distribution of the coordinate, like wave function. And here it is this collective Hamiltonian, which is a function of both this potential energy as well as the collective inertia. Now, it has also limitations, like here we cannot have any kind of wave function. There is certain prescription for this wave function. Normally Gaussian type of wave functions we can treat using this method. And also, this method, if we apply for very large lifetime, then it takes huge time, which is basically makes it impractical to apply for tunneling. Also, we have this method which is called McNeek method. Basically, here we calculate this potential energy surface, macroscopic microscopic interactions. So basically, macroscopic part comes from the liquid of calculation, and then shell correction is included in that. And one can solve then the whole dynamics, additional collective dynamics. When we solve or Lyapunov dynamics kind of equation, which includes fluctuations, and it gives a final field distribution, also the probability. So in that way, we can field distributions. This is one global survey of this type of calculation, where actually this plot shows the peak of the heavy fragment masses, and here I showed it to just to demonstrate that this type of calculation can be used for this type of global survey. But there is again such limitations are there. So if we go for very heavy systems like for fermium, we can see that this red curve is the model prediction, and these gray lines are actually the results data. So we can see there is large deviations if we go to very heavy systems. This is because these interactions are mainly optimized for stable systems and very neutron-rich systems, which are basically of interest for our process calculation. Then this type of theory may fail. Also, this is a classical theory, so we cannot have tunneling picture inside. So, what is our theory? What we are going to apply is something like this. So, for the spontaneous fission, so we know that for our process calculation, we need either spontaneous fission or neutron-induced fission. Now, for the spontaneous fission, we can solve the problem by using the WKB approximation. So here we calculate the tunneling probability using the WKB, calculating the WKB pathway. And in case of induced fission, we know that here it is induced fission, so the total excitation is quite low. So we can actually calculate the minimum energy pathway to get the final value. So now I will tell more about this WKB pathway and how it is actually done. So this WKB method gives us this spontaneous fission half-life like this, where this n is the number of pascals of fission barrier per time, which the value comes around for 20. That, and then this probability is penetration probability. It comes from this WKB calculation, and this P is function of this action integral, where this action involves the effective inertia and the potential. And here I've shown the schematic of that. So this is a two-dimensional surface, and this region is the barrier region. Then we have this inner turning line, and there are many possibilities. So our task is to calculate the minimum action path on this surface, and this minimum action path will give us the probability. And to do that, we need this effective potential and the inertia. These we can calculate using consistent static DFT theory. So this is the method I have just schematically shown. So we normally solve this HAP equation, and this equation is function of, again, this generalized density and this single part. It involves also single particle radium and single particle energies, and this equation can be rewritten like an eigenvalue equation, where this W is functional of the density, and these densities are again function of the quasi-particle wave functions here. So this is nonlinear equation, and we solve it iteratively. And when solving this equation, we can add constant in terms of these multiple moments. These multiple moments, value of these multiple moments actually point on the potential energy surface. So if we repeat the calculations with different values of these multiple moments, we can generate the whole surface. And also this nuclear pairing is an important input here. So we normally use this mixed pairing interaction, factor for this mixed interaction. We use it for fission calculation. Then after obtaining the energy, we need to know the inertia. So we apply adiabatic time-dependent Hartree-Fock-Bogoliubov approximation. So it is basically derived like this. So here I've written this. This is the time-dependent Hartree-Fock-Bogoliubov equation. And if we do an expansion of this R, this generalized density in terms of this collective momentum, and if we take low momentum approximation, then we can just keep few lower order terms. So these terms are like time event, time mode, time event, like this. It is, and corresponding energies can be expanded like this. And if we use this expansion in this equation, then we can express the kinetic energy in terms of this expression. And if we compare this expression with the standard form of kinetic energy and standard, so here this inertia is coefficient of quadratic of the collective coordinate. And if we compare these two, we can get the expression for the collective inertia. And if we now generalize it to multidimensional surface, multidimensional coordinates, then it is generalized like this. Now here it involves this time or density, so we cannot generate this time or density using static solutions, which involve only the time event solution. So we often apply the cranking approximation, where this time or term is neglected, and we get this compact form, which involve these F matrices, which are basically coordinate derivative of this density. These are static densities, this is rho 0 and kappa 0. This is pairing density, this is mean field density. And then this involves the derivatives with respect to the coordinates. So we need to calculate these densities very close by points to calculate these derivatives. And to avoid this, we often apply this perturbative cranking approximation, which actually can be expressed in terms of these moments. And here only we need to calculate the expectation value of the moment in the quasi-particle basis and the quasi-particle energies. From there, we can get the calculation, magnitude or value of the collective inertia. So these expressions are often applied. So I will mainly discuss the results, what we get using this perturbative cranking approximation. And this cranking approximation is important maybe for this lifetime calculations, which I will not cover in this. So basically here R is time dependent R, and then we have like it is a function of also this momentum, and then we expand this momentum terms, and then it will be like expansion in terms of momentum. So this is collective momentum, and this is the zeroth order term, and then we have this time order term. So this is time order because of the presence of the momentum. So momentum because it involves that moment collective. So this I have not written that explicitly here, but these are basically coming from that expansion.
So it sounds like none of the
yes, so it is basically it is like some exponential of I type T type of term. So there are two this is like we first express it in time reverse frame, and then we expand it and we get different terms like that.
Okay, this has nothing to do with any personal family or the same.
Actually, when we have motion, so that means we are basically breaking the time reversal symmetry. So it is in general is neither time even nor time. But when we expand it, that's why we have on also time even and time on, because there we cannot apply the time reversal symmetry because it is the we are talking about dynamics. Something is moving. So in that way, it is the symmetry is broken. Now, when we expand it, and then we find that the final expression will come in terms of time even as well as time effect. So it is there, all the terms will contribute. So once we have the inertia as well as this potential energy surface, then the next task is to get the minimum action pathways. And here I have written old method to calculate the minimum action pathways, because after a few slides I explain what method. Now in this old method there are two ways we can calculate these pathways called reach method. Here actually the path is expanded in terms of the functions, and these coefficients of the sine functions optimized to get the minimum action path. And in case of this dynamic programming method, we divide the whole space in a small rectangular grid, and then from the initial point to final point, we just move layer by layer, and in the process, we always optimize the path in such a way that it gives the minimum action up to a certain layer. So in that way, we proceed and final point. So this is sequentially we reach there. So we normally use this method because this proves to be more useful compared to this method. And this is one example where we applied this dynamic programming method to get this minimum action path. This is the 240 plutonium surface, and this blue line is basically this DPM path, and also this dashed line is a static path, and we have seen that for this type of system, dynamic path is very close to the static path. This is just a representation of this method, how we do. And then now I come to the calculation of the yield distributions. So what we know now, we have the pathways, we know the potential energy surface path. Now next task is to get the fission fragment yields, and there are many methods. So I should say that, like I have already told about this Brownian shape motion. Then there is fission point model, and also there are phenomenological model like ABLA and HTF. These are regularly used for large scale calculations. But the point is that if we compare these different models, we can see that there is large discrepancy between different models. This is yield calculation for 284 Copernicus, and we can see that different models really predict different yield distribution. Like in our calculation, we get cluster TK for this type of nucleus, and we get very well separated. This is like a cluster, and this is a very heavy fragment. But in other models, we get symmetric distributions, whereas this DSM predicts a very broad distribution. On the other hand, this fission point model, which does not involve any dynamics, it gives a very narrow and sharp peak, and also gives similar. So there are discrepancies in different models. So we need to find a method which is more accurate and precise to the efficient yield distributions. And with that aim, we proceed. And before going to the exact method, let me explain what we really use in that calculation. It is, yeah.
Previous slide.
Yeah.
So in that window, but that means that outside the window, there's no yield.
Yeah, it is within that. So we use the nucleonic localization function. This is a function which involves not only the scalar density but also the kinetic energy density, also the current density. And in case of static solution, this current contribute actually, but it gives us the information of the nucleonic localization. So basically, it measures the probability of finding nucleons with the same spin at the same spatial localization. And like it says, so if we get this C equal to 1, that means this part vanishes. So in that case, that means there is only one nucleon with the particular type of spin and isospin. And this actually happens in case of like helium, where we have only a single particle with a particular spin. And on the other hand, this C is close to half for a unit of homogeneous Fermi gas. So the value of C between half and 1 actually determines how the nucleons are distributed. And here, this is compared with the density distribution. So this panels, these are the density distribution, and the left one is NLF distribution. We can see here that especially for this 8 beryllium, we can see the density is like elongated folate type of shape. But if we look into this NLF distribution, we can really identify two alpha cluster inside this beryllium. Similarly, in case of oxygen, I mean, it is told that it has a dip in the density at the center, but it is not visible in the density. But if we study the NLF, we can see that there is some dark region which gives a lower density at the center. And also for like this 20 neon, it is 10 proton, 10 neutron. We can find like carbon-like structure with 2 alpha kind structure here. So this NLF actually gives a good prescription to identify internal structures of like nucleus. And this method also applied in case of fission. So here I have shown the 5 configurations along the fission path of 232 thorium. And we can see that this upper row is basically density, and then this one is NLF. And we can see structures which are appearing in the NLF, but in densities we don't have such structures. And if we zoom into it, we can see here like this is the fragment, and if we compare it with the corresponding, these are basically corresponding densities, and this is the NLF of the fragment. And we can see well pronounced structures in the NLF which are not present in the density distribution. And not only that, if we follow the path, we can see that this type of structures are really appearing well before the scission. So at least this outer part. So this actually hints us that we can really use this type of structure to define the fragments well before the scission actually occurs. And we apply this to different systems. Here I have shown how it can be applied. Like here, this NLF is calculated at the outer turning point of this 240 plutonium nucleus. And we can see that this upper part has concentric circular structures appearing here. And then if we just consider this upper half, this outer hemisphere, and we calculate the number of nucleons inside it, we just then double it to get the prefragment. That means some kind of fragment structure which is already appearing inside the nucleus. And we calculated it, and for 240 plutonium, we got that for the lighter fragment it is 80 germanium, and for the heavy fragment it is 128 tin. And then we calculate localization for these systems, and and here we can see that for this localization of this steel is really matching with that of 240 plutonium, especially in this outer part. So it actually confirms that this type of structure are really formed well before the scission at this outer turning point. So this gives us the idea that we can really use this type of structure to identify the fragments even without continuing the dynamics up to scission. And we
Can you explain what is the difference between our point and scission point and what's happening?
Oh, this is basically the barrier region, and this is the ground state. So this outer turning point is basically the region where we do the tunneling. So this is the outer turning point for the WF. And it is not the point where actually nucleus breaks into two parts. So scission is basically the configuration where we have pronounced two fragments. And this is the point where we don't have two fragments. So we choose this point to calculate this prefragment.
So in fact, the KPC doesn't have the Kuma predict the national.
Yeah, because this region is the classical region. So once the system reaches here, this region, we can have like it here energy is more than the barrier. So it is classical region. So we can do classical dynamics here or any kind of quantum dynamics, but WKB is giving us this at the outer point. And especially for very heavy systems, this region is quite low. Because this after the barrier, for heavy system, this barrier is quite low, and that's why this region is quite, it is not very large. Then from this point, this outer turning point to scission, this region is quite long for heavy. Now, not only this localization function, so we also we actually check that these prefragments are we calculate these prefragments for different nucleus, and we found that one of these prefragments is really close to this shell close system, like 82, and this is Z50. So these are shell close. We have shell closure at this point. So one of the prefragments is really close to this shell closure. And not only that, if we estimate the single particle levels from the outer turning point to scission, we can see that this dashed line is the Fermi energy, and we can see that there are no level crossings near this Fermi energy. So we can assume that these prefragment structures are really stable. This continues up to scission. And with this idea, if we put these are basically the density distributions. So we can see the density distributions when we use the fragment densities. Then we left with some net nucleons. So that means the nucleons which are near the region, not localized in the prefragment. Now the whole task is to how to distribute these net nucleons to the two fragments so that we can the final fragment. And for that we use statistical answers. So this is just a statistical probability we use to get these nucleons distributed among the two prefragments. And here this ER is basically the residual energy which is calculated using Sadhukhan model. So we assume what we found, that the shell is actually stabilized at the prefragment, and the rest of the dynamics is like depending on the what is the force is basically coming from the liquid drop force, which is Coulomb force, and the surface force, and maybe the average pairing force. So all these can be incorporated here in this energy, and then these distributions may be decided through this probability distribution. So this is the statistical microeconomical statistical probability. So this is the whole scheme. So we start here the ground state, and then we reach here through WKB pathway calculation, and this is the outer turning point. At this point we stop the dynamics. We know the shell structure is stabilized, and this rest of the path we don't calculate. We use statistical distribution to get the final fragment, and to get it we need this residual energy, which involves this liquid drop energy as well as the average pairing energy. And if we use this method and get the fragments, these are the results. So here we can see that this blue band is our result, and these dots are basically experimental data. And also we compared it with other models, like this black line is a fission point model, and then this gray dash line is a Brownian shape motion. So we can see that our result works pretty well compared to the other models prediction. Like here we have broad distribution from the fission point model, broader distribution for fission point model, and Brownian shape motion, but our results are the experimental data. And not only that, we can really reproduce this odd even staggering in the charge distribution to this average pairing. So we can see this is for uranium, plutonium, and even for this heavier system, we can reproduce the data. So this gives us the confidence that this simple model, hybrid model, really works, which includes the dynamics as well as the statistical distribution, which incorporates this excitations, how to handle the excitation. So this actually our model calculation, and not only the yield distributions we can calculate, like these NZ distributions, and here we can see that all given staggering, and here this is isotopic yield distribution. So for each of these Z we can calculate the what is the mass yield, and here these zigzag lines are basically calculation before neutron evaporation. And then if we use simple neutron evaporation picture, like just energetics, and from energetics if we calculate the neutron evaporation, then we end up with this black curve, which really agrees well with these dotted dots, which are the data. And we can also calculate something called charge polarization, which measures the difference in isospin, like this Z. This is Z for this compound nucleus, and then we can calculate the average Z for all the fragments for a particular mass. And then if we take difference, it gives us the how the charge polarization is different from the compound nuclear N by Z. So here these dots are the data, and solid line is our calculation, and then this blue line is fission point model. And of course this Brownian shape motion does not, it is not capable of calculating this charge polarization because it assumes the N by Z to be conserved in the fragment. So that's why we can see that our results are really agrees well with all these different observables. So this is a table which shows what we can really do and what we really need compared to other models. Like we can calculate odd even staggering. Our calculation involves dynamics because we calculate the WKB pathway which are driven by the dynamics, and then we use microscopic potential energy surface. Still we don't we can calculate the kinetic energy distribution, but still it is not incorporated in our model. And another important point is that in our model we don't require any information of the scission point. So deciding the scission is a critical thing in the fission studies, and we don't require scission point because we in our calculation at the after turning point, and the rest of the dynamics is rest of the part is governed by the statistical distribution. Now, with this, now I come to the next progress. So that is what we apply for the least action pathway calculation. And here I will explain what is our new methodologies for the pathway calculation. So this method is this work is basically done by Dick and Daniel. Here we actually use this nudge elastic band method to calculate the least action pathway. So this method relies on this calculation of the steepest descent on a potential energy surface. So now if we replace this V with the action integral, we get the minimum action path or this least action path. And here this is a video which shows the difference between the minimum action path and the least action path. So we can see that this red line is the minimum energy path, and this least action path is not necessarily we go through the minimum path. It goes through, I mean, it also minimizes the path length. So this line is the least action path, and this red line is the minimum energy path. And when we apply this for realistic systems, so this is calculation for 232 uranium. And if we compare the action values with respect to other methods, we can see that it works well for different nucleus. So it is giving more or less similar or lower value. So it actually confirms that this method is really useful for calculating the fission pathway. And the most interesting of this NEB method is that it can really estimate different pathways if those are present in the potential energy surface. So we call it like multimodal fission. So if we have more than one mode, then this method really can decide the different pathways. So we can see if we start from different initial points, we ultimately end up with the two exit points which give two different modes in the on this toy potential energy surface. Now, if we apply this method in realistic calculations, where these energies are calculated using different functionals, we can generate different pathways like one is asymmetric path, one is symmetric path, and these calculations are going on at all these pathways. And what we can see is that we can actually calculate the relative probabilities of these pathways, like what is the probability of this asymmetric fission and symmetric fission. So these relative probabilities we can calculate, and these are the relative probabilities for the symmetric pathway. So we can see for 254 fermium, it is always asymmetric. Symmetric probability is 0, and that's why we always get the asymmetric distribution here. But in case of say 258 fermium, this is the interesting case where bimodality is already seen experimentally, and we can see that this immediate functional is giving 0.8% asymmetric symmetric fission, then 20% is asymmetric. So if we combine these, we get like a symmetric peak and also a tail part. So this type of calculation really gives us the yield distribution for multimodal fission. This was what is under progress. And this is a similar calculation in 3D. So here we have not only this 20 Q20 Q30, we also have moment which actually decides the net thickness. So this we know Q20 is elongation and this is mass asymmetry. This like this red line which ends up at this point, and the corresponding this surface is outer turning surface, and at this outer turning surface this is the localization, and this yellow line is elongated mode, so that means it has higher Q40, so it gives this elongated. So we can see the difference between the configuration of these modes, and we can in 3D we can really calculate different type of modes, and these are again calculated by Eric and Daniel. They are doing these calculations, and we can really identify different modes and the corresponding probability. So still this work is going on, and we are getting some interesting output from this physics. So with this, let me just summarize. So what we learn is something like this. What we are getting from all these developments like this. So 7 years back, we know that we can calculate the field distribution. There we have used the multi-dimensional 3D surface as well as non-perturbative cranking inertia, and calculation takes around 1 to 2 months with 1 million CPU hours, and we get these distributions. And here also these pathways are calculated using the dynamic programming method, and then plausible dynamics is done to get the yield distribution. Now, after all these developments, so where we now is something like this. So now we can calculate the potential energy surface, and of course we can use this perturbative inertia, not this non-perturbative inertia, and it reduces the whole time drastically. Also the computational usage is reduced drastically, and we can really calculate this NED pathways quite fast, and we don't need any dynamics further, and we get this type of distribution. So we can compare that precision wise, these are quite good. So we can actually so what we gain is this time saving. So now we can really get this type of distribution in a week what we were getting in taking months. So this is the whole saving, time saving as well as money saving, and we can now do large scale calculations. So our future plan is something like this. So for the yield calculation, we are equipped for large scale calculation, but we can also apply, we can also explore different AI based method to optimize this potential energy surface, or maybe even make it even faster. But in case of fission half-life calculation, this shortcut, still we don't have any shortcut. So we need to minimize the action integral at least using these coordinates, then only we can get the current action integral, and then we need precise inertia to get the action integral, and time inertia will be a possible choice for this. And also there is uncertainty related to point energy in the action integral. So this integration is so we need to work on the half-life to get it for large scale, ready for the large scale calculation. So with this, I'd like to thank my collaborators at MSU today. So they are my current collaborator who really helped me to get on this. And thank
you. Very impressive work. Is statistical on the so you get to the other point. How do you use statistical models to determine the drivers? How exactly, what is the information that goes into statistical models?
well, so let me go back to this. So this is the equation. Basically, this is microcanonical probability. So we have these three fragments. these two peak fragments we have. Now what we actually calculate, suppose these are the net nucleons. Now these net nucleons we distribute among these two peak fragments according to this probability. So what we do, we search for different possibilities and calculate the corresponding probability. And each of these distribution give us a certain probability. And that probability is basically we get in this distribution. So, and to get this probability, we need only this, like how many particles we are putting in each fragment, that actually decides these masses. And additionally, we need this energy. So
What comes from some models?
it is just microcanonical probability if we have two fragments and if we calculate the number of states, then from there it is coming.
So this is not our expression.
Yeah.
This was developed by time, quite long time ago. So this is a classical expression. This is like having two containers, right? And with an extra part, so we have to distribute it over those two containers, assuming micro count.
Those extra nucleons don't fly away. The neutrons don't fly away.
Well, so these are doing spontaneous fission, at least up to getting the fragments, they don't fly away. That is as. But there may be one or two nucleons that may fly away. Not more than that.
So then they show the yield of the fragment. There is some amount of profit in that.
Yeah. And then also we can use like simple answers for this neutron evaporation. So this is what we get after neutron. So once we have the fragments, it has excitation energy, and then we calculate the neutron separation energy for each of these fragments. And we can just emit neutrons up to that energy goes below the separation. And in that way, if we do, we can see that this curve really smoothen out. So this zigzag curve is without evaporation. So when the evaporation we take into account, this curve actually smoothens.
So the two fragment configuration is more like a doorway state.
Yeah.
And then the decay sort of neutron evaporation. More questions?
Well, thank you for the micro. So when you see those two fragments, I mean, you showed us a figure with the shells, seals, and states. How can you know, like, when you said that the configuration standard of these fragments, how can you like?
No, this is not after scission. This is calculated before scission.
Oh, that is before.
Yeah, so it is outer turning line to scission. So this is the simple part. It is single one.
Question related to that. So these calculations that you showed are coordinate space or harmonical space?
This is harmonic oscillator.
So this harmonical space was done.
No, we have not studied because there are like two harmonic oscillator basis is there. That type of potential is there. But since we are not going beyond scission, two center potential is there.
The whole idea, we do not have to go to scission.
Yeah.
You know, scission is difficult.
Yeah.
Very unpleasant, you know, we are breaking glucose into food.
But if you want, you have to change the data. You have to formulate the data.
And can do, basically, do calculations in that box in 3D coordinates. This is where we are heading.
Yes, 6.